Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to continue talking about the Bootstrap. In a previous video we showed how to use the Bootstrap to estimate standard errors, which can then be used to build confidence intervals, assuming that the estimator of interest has an approximately Gaussian distribution. In this video we're going to show how to build confidence intervals directly using the Bootstrap. And we're also going to show that these confidence intervals can be applied to a certain kind of estimators that do not necessarily have a Gaussian distribution. Let's get to it. We're going to talk about Bootstrap confidence intervals. Let's remind ourselves about our ultimate goal, which is to estimate population parameters from random samples. So here we use this example in many of the videos. We have a population of people and the heights, in particular the heights of a population of people. I want to estimate the population mean, but we only get to see a subset of n samples. Here, the population parameter that we want to estimate is fixed, but every time that and by this time I have repeated this in many videos, but I think it's important to give the proper context at the beginning of the video, so sorry if this is getting a little bit boring. Every time we obtain n samples, the sample mean is going to change, okay? Here we see 3 examples of 400 samples from this population. Every time we get a different sample mean. If we were able to do this many times, we would be able to quantify the uncertainty associated to our estimate very well. But of course we cannot do this. So here I'm showing you a histogram obtained from 10,000 subsets of size 400. In practice we have one subset of size 400 because if we had more samples we just use them to get a better estimate. I hope that makes sense. Our goal is to quantify this uncertainty just from the 400 available samples. In order to do that, what we do is we build a confidence interval, which is a range of values that contains the parameter of interest with high probability, often 95%. Let me remind you quickly what the logic is of these confidence intervals. In the case of the sample mean, we know that the sample mean is approximately Gaussian, has an approximately Gaussian distribution centered at the population mean, and that its standard deviation can be computed from the population standard deviation and from the number of measurements. And with that, we can obtain an interval here that is going to contain the sample mean with probability 0.95 or whatever probability we desire. Of course, in practice, we only get to see the sample mean. But if we are able to estimate this width here, we can actually just build an interval centered at the observed sample mean that has that width. And now if the population, if the sample mean is here with probability 0.95, then immediately this guy, which is at the center of that interval, is going to be within this interval that has the same width but is just shifted with probability 0.95. That's the whole logic of building confidence intervals. Okay, so here are some confidence intervals built in this way for the sample mean in our height example. Okay, so where does the Bootstrap come in? The Bootstrap actually allows us to estimate the standard error, which allows us to estimate this width for estimators where we don't have a formula for it. In the case of the sample mean, we do have a formula. What is the logic of the Bootstrap? Well, we take our samples, our n data points, 400 in the height example, and we treat them as a new population from which we sample independently and uniformly with replacement. So each of the Bootstrap samples is going to be equal to one of these guys with the same probability, and we sample each of them independently to obtain a new batch of n measurements in this way. Okay, that's like a Bootstrap batch of n measurements. How do we compute the standard error from this? Well, basically we have these n samples. We take a look at the value of the estimator. Then to compute the Bootstrap standard error, what we see is the variance of the estimator, but computed on Bootstrap samples. Okay. Typically, via the Monte Carlo method, where we basically take Bootstrap samples, we compute the corresponding estimator. More Bootstrap samples, we compute again the corresponding estimator. Notice here that the original samples are in gray, those are going to stay. these other guys are the Bootstrap samples that we obtain by resampling from the gray histogram. Okay, and every time we resample, we obtain a different Bootstrap sample mean. We do this many times, and eventually we have a distribution of Bootstrap sample means or Bootstrap estimator if we're applying this to another estimator. And from that, we can just estimate the standard deviation of that estimator. We would love it for this Bootstrap distribution of the estimator to be close to the true density of the estimator, which we do not have access to because we cannot repeatedly sample from the underlying population, as I explained a moment ago. Okay, so in this case, these two distributions, in the case of the sample mean, are going to actually have a pretty similar standard deviations. So this is the Bootstrap standard error, and the true standard error, which is the population standard deviation divided by square root of n, is equal to a value that is pretty close. Okay, so now we're going to see how we use this to build a Bootstrap Gaussian confidence interval. We take our n samples, we take our value of the estimator obtained from the n samples, we approximate the standard error using the Bootstrap, and we basically multiply the standard error by a constant that gives us the adequate width. If the width that we want is 0.95, then that constant is 1.96. All right? And like that, we can build a Bootstrap Gaussian confidence interval based on the Bootstrap standard error. We applied this in the previous video to the population correlation coefficient of this example, where the true population correlation coefficient is 0.718, and we only have 100 samples. Okay, and this is the sample correlation coefficient of this specific 100 samples. Now the goal is to quantify the uncertainty about this guy just from those samples. Basically, what do? We're going to apply this technique where we're going to estimate the standard error using Bootstrap and then assume that this guy is Gaussian. This is going to be okay because this guy is approximately Gaussian. Approximately, right? The approximation is not amazing, but it is approximately Gaussian, and now we're going to try to estimate the standard deviation of this Gaussian using the Bootstrap standard error. Okay, this is the Bootstrap distribution, and this is the true underlying distribution. They do have similar standard deviations, okay? So you can see that the standard deviation approximation obtained by the Bootstrap is actually pretty good. You can also see that this is not exactly Gaussian, which is going to be our assumption, but this is a motivation for what comes next. Okay, so we take a look at the Bootstrap Gaussian confidence interval for the correlation coefficient. We have our sample correlation coefficient, we plug in the standard error obtained by a bootstrapping, and we choose the adequate constant, which in the case of 0.95 is 1.96. And that is going to give us this confidence interval for our specific example. In the previous video, at this point, I think I said something like the correlation coefficient has to be between 0 and 1. Of course, I meant the magnitude is between 0 and 1. The correlation coefficient is between -1 and 1. I cringe when I listen to my videos. I don't usually listen to my videos very much, but sometimes I listen to some random parts where I'm checking that the sound is okay, and then I listen to something like that, and I'm like, oh my God. So anyways, sorry about that, but let's move on. Okay, so here we already saw in the previous video that things work out. We get a pretty decent confidence intervals with good coverage. We're happy. Now what happens if we only have 25 samples and we want to, again, quantify the uncertainty around this sample correlation coefficient? It's the same population, okay? If we apply our Bootstrap Gaussian confidence intervals with the standard error obtained via bootstrapping, the coverage now is 90%, not so great. Why is this happening? Here you can see this is, maybe I should have made this clearer, right? But this is a true population correlation coefficient, and we see quite a few confidence intervals that do not contain the true population correlation coefficient. This is what we meant by coverage, in case that was not clear. Okay, this happens 90%, so the true population correlation coefficient is within the intervals 90% of the time. It should be 95%. So what's going on? Well, what's going on is that this estimator is not Gaussian, like the Gaussian approximation is not that great. as you can see here. The distribution is actually pretty skewed. And this is known to happen for the correlation coefficient. So now our challenge is to build confidence intervals that we can apply to non-Gaussian estimators such as this one. And we're going to see that there's a certain type of correlation did I say correlation coefficient? I meant confidence intervals that we can apply to estimators such as this one. Hopefully I said that right. If not, well, I said it again. It turns out that there's a type of confidence interval called the Bootstrap percentile confidence interval that can be applied to the correlation coefficient and other estimators that are not necessarily Gaussian. The reason is because they can be transformed to have a Gaussian distribution by a monotonic transformation. We're going to talk more about that in a moment, but first let's explain what is the logic behind these percentile confidence intervals. And for that, we're going to go back to the sample mean. Okay, so the logic here is going to be, we're going to see that things work out for the sample mean and for estimators that are approximately Gaussian, and then we're going to see that we can extend that to non-Gaussian estimators. Okay, so the sample mean, what do we know about the sample mean? By now I've said this 1,000 times in other videos, but basically if we try to approximate a population mean from n samples using the sample mean, we know that this is an unbiased estimator, the mean is at the population mean, and the standard error or the standard deviation of the sample mean scales with the population standard deviation divided by square root of n. Okay, you're probably tired of hearing me say this. And what is the distribution of the sample mean? Well, it's Gaussian by, approximately Gaussian by the central limit theorem. All right, so now we're going to compare this to the distribution of, to the bootstrap distribution of the sample mean. Okay, what's the bootstrap distribution of the sample mean? Now, the data that we have, the n data points that we have, are the population. And what we do when we apply bootstrapping is we obtain bootstrap samples, batches of n bootstrap samples from that population, and we compute their average. What is the mean of this bootstrap sample mean going to be? Well, it's the mean of the population, which in this case is the sample mean of the data, no longer the population mean. What is the variance of this sample mean? Well, it's the population variance divided by n. And here what we see is that the population variance is very close to basically the sample variance of the data that we're observing. Okay, there's just this n instead of n minus 1. If n is large enough, this is going to be a good approximation. This is well approximated by the population variance divided by n, which is the same variance of the actual sample mean. And this is going to be very important. Now, what is the distribution of these bootstrap sample means? Where we're sampling over and over from a population. We can take the Gaussian approximation provided by the central limit theorem. We're going to have something that is Gaussian with that mean and that variance. So basically, what we're saying here is that this underlying true distribution of the sample mean is Gaussian, centered at the population mean and with a standard deviation that is the population standard deviation divided by square root of n. And this other guy, which is the bootstrap distribution of the sample mean, is going to be centered at the sample mean of the sample, so it's shifted because of that, but its standard deviation is actually approximately equal to the standard deviation of the true density because it's the sample, its variance is essentially the sample variance divided by n, which approximates the true population variance divided by n as we go to infinity. Okay, hopefully that is clear. And both of them are approximately Gaussian. Okay, here you see that their standard deviations or standard errors are actually quite close. So you can think of them as two Gaussian distributions that have the same standard deviation but are shifted with respect to each other. So now we're going to build a confidence interval based on that on that logic. I'm going to first draw how we're going to draw this, how we're going to build this confidence interval, and then I'm going to show you because I think it's just so much more intuitive to draw. So imagine that you basically find 2 points here such that the amount of probability that remains in this histogram is 0.05 0.95. Okay, then basically this is an interval that is obtained by shifting an interval here that has probability 0.95, because these are two Gaussian distributions that have the same standard deviation. And this is exactly how we build Gaussian confidence intervals to begin with. So this guy is actually going to be a valid confidence interval for the population mean. Okay, so hopefully, I mean, I'm going to explain this in more detail. I just wanted to give you like a visual idea of what we're going to do. So we have these n samples, we have the estimator, okay, which we're like focusing in the on the sample mean for now, but any estimator that has a Gaussian distribution is would be fine. And now we get bootstrap samples, and we look at we find 2 points, which are the alpha halves and 1 minus alpha half percentiles, so that between them we get 1 minus alpha probability. Okay, like the bootstrap estimator is there with probability 1 minus alpha. That is going to be our percentile confidence interval. Okay, we're going to say that that interval is going to be our percentile confidence interval. We still need to show that the population mean is going to belong to that interval with probability 0.95, with probability 1 minus alpha. I said 0.95 because we always set 1 minus alpha to be 0.95. Why is that the case? Well, if the bootstrap sample mean is Gaussian with mean equal to the sample mean and standard deviation equal to the approximately equal to the population standard deviation divided by n, then we obtain an interval which should look quite familiar. We're taking the standard deviation of the actual population mean, the actual sample mean, and we're multiplying it by a certain constant so that the interval contains 0.95 of the probability. This is exactly a Gaussian confidence interval for the sample mean. So let's remember that logic. In the logic of Gaussian confidence intervals, what we said is, if we know this width, then what I can do when I get the sample mean is just center the interval at the sample mean, which is what I'm seeing, and that's going to contain the population mean 0.95% of the time. And what we're saying is that if we assume that the bootstrap distribution is exactly centered there and has the same standard deviation as that guy, well, this interval that we're obtaining by shifting is exactly the one that we obtain by making sure that we have 0.95% of the probability of the bootstrap distribution there. Okay, so it's exactly equivalent to what we were doing when we were building Gaussian confidence intervals under this assumption that the bootstrap distribution is indeed Gaussian and has a standard deviation that is close to the standard deviation of the underlying estimator. Okay, I meant the standard deviation of the estimator obtained from random samples. Okay, so hopefully that makes sense. Of course, how do we compute these percentiles? Well, we just take a Monte Carlo approximation. We generate many batches of bootstrap samples, and we basically compute the parameter estimates corresponding to each of the batches. And now we come up with percentiles so that out of these guys, 95% are within the percentiles. Okay, hopefully that makes sense. If we're interested in a 95% confidence interval, a 0.95 confidence interval, we're going to pick the 0.025 percentile on one side and 0.975 percentile on the other. I don't know why I did that to myself, but hopefully you get the idea. Okay, so now we have shown that this logic holds, like we're going to get valid confidence intervals with this bootstrap percentile confidence intervals, as long as the estimator has a Gaussian distribution, and then the bootstrap distribution is also Gaussian and shifted from that Gaussian distribution. But now you will tell me, okay, Carlos, like very interesting story, but the whole point of this was that we had a situation where this correlation coefficient actually did not have, the sample correlation coefficient did not have a Gaussian distribution. So come on, let's try to address this issue. And we can actually address that issue because in the case of the sample correlation coefficient, if we apply this monotonic transformation, which is called Fisher's transformation, we can actually map it to have a Gaussian distribution. This is the transformed correlation coefficient once we have applied this monotonic transformation. It's not obvious why this happens. Fisher was a very smart person and he figured out this formula. We're going to show that the Bootstrap percentile confidence intervals are going to work when this happens, when we have a monotonic transformation that transforms the estimator so that it has a Gaussian distribution. But the beautiful thing about this is that it does not require knowing the transformation. The transformation just needs to exist, which is quite amazing. Let's see why this is the case. Okay, so imagine that we have a population parameter gamma and then an estimator g of gamma. We're going to assume that m of g, where m is a monotonic transformation, that we're going to assume is non-decreasing, but the same argument holds for non-increasing transformations, is Gaussian with mean gamma and variance sigma squared for some monotonic m. Okay, so this m exists, we don't need to know it. Once you apply this m, your estimator becomes Gaussian around, there always has to be a typo. It should be m of gamma. Okay. Where if we apply m, we're Gaussian around m of gamma, where gamma is the population parameter we want to estimate. Okay. Conditioned on a certain value of the estimator, we can obtain a bootstrap estimator by resampling the available data. And that bootstrap estimator is going to be Gaussian once we apply the transformation with mean m of g, and remember that this is m of gamma. So the idea is that both for the original distribution of the estimator and for the bootstrap distribution, if we apply this monotonic transformation, we have exactly the same situation as we had earlier, where we get these two Gaussian distributions that are shifted with respect to each other. Okay? We're assuming that once we apply this monotonic transformation, this happens, and this is approximately true actually for the correlation coefficient. Okay, great. So now let's see what we can show about the percentile confidence intervals. So let's define gamma prime as m of gamma and g prime as m of g. And remember that these are the centers of the population distribution, the estimator distribution once we apply the monotonic transformation. And this is the center where we condition on a specific set of samples. So now, from our previous discussion, we know that if we have transformed the data, then we can obtain a valid confidence interval by just applying the percentile confidence intervals. Okay, by this argument where you shift the Gaussians, things work out. The probability that your transformed parameter is within the percentiles of the transformed estimator obtained with Bootstrap is going to be 1 minus alpha. We have just applied this result that we derived earlier to this case where things have been transformed by a monotonic transformation. But now what we realize is that we need the alpha half percentile of MW conditioned on G, okay? Just to be very clear, this is the Bootstrap percentile of the transformed data. But now, because this is a monotonic transformation, the alpha halves percentile of the transformed data is equal to the monotonic transformation applied to the alpha half percentile of the original data. That's not completely obvious, and you probably, should look at this equation and make sure that you buy it. But the idea is that if M of W, where W represents bootstrap estimates, the estimator obtained from bootstrap estimates, is smaller than M of Q, because the transformation is monotonic, this immediately implies, and the implication is in both directions, that W is more or equal to Q. Because of that, this means that this guy, M of Q alpha halves, is actually equal to the alpha halves percentile of the bootstrap percentiles after applying the monotonic transformation. This is as clear, I think it is as clear as I can explain this. You actually maybe should go through the equations yourself. But at a high level, basically the idea is that these monotonic transformations preserve percentiles. So we were applying this argument of, you know, the Gaussian shifting, and then you get a valid confidence interval. We can apply that to the transformed data, but then we can bring it back because the monotonic transformation preserves percentiles. And now we have a situation that because of that, okay, this is showing that if you look at the alpha half percentile of the transformed data, it's just the monotonic transformation applied to the alpha half percentile. You can do the same for the 1 minus alpha half percentile. And then you get that the probability that the transformed population parameter is within these guys is equal to 1 minus alpha. But we're not done yet, because this is the actual, so these are the, just to be clear, these are the bootstrap percentiles that we can compute from the original data, but we have applied the transformation to them, right? Oops. We have applied the transformation to them. But this guy is also the population parameter after applying the transformation. So this immediately implies that if this guy is between these two guys, then gamma has to be between the alpha half percentile and the 1 minus alpha half percentile by the same argument as before, where this is a monotonic transformation. So in particular, if this guy is smaller than this guy, then it's also like, then this guy is smaller than that guy. I realize that this, you know, this is not super easy maybe to understand if it's the first time that you see it. But, you know, the main takeaway is we have this logic that shows that percentile confidence intervals obtained from bootstrapping work for Gaussian estimators. If we know that the estimator is Gaussian after a monotonic transformation, because monotonic transformations preserve percentiles, then the argument still works. Okay, hopefully that makes sense. And now I'm going to show you how this enables us to at least partially correct the confidence intervals that we obtain for our 25 samples. Here you can see that, so in gray I'm showing you the Gaussian interval, and in black I'm showing you the percentile interval. And in general, the percentile intervals, as you can see, are more asymmetric, and some of them are actually successful when the corresponding Gaussian interval is not because they automatically adapt to the shape of the underlying estimator distribution, because of the argument that I just explained, because that distribution can be mapped monotonically to a Gaussian. And when we look at the coverage probabilities, we have improved them quite a bit, you know, by more than 2%, which is not so bad. Okay, and so this is the coverage probability, how often the population population correlation coefficient is within the confidence intervals that we compute. It's better for the percentile one than for the Gaussian, because again, like, this doesn't work out very well because the correlation coefficient is not approximately Gaussian. This works out better because it is approximately Gaussian after a monotonic transformation, but we don't need to know that monotonic transformation to compute the confidence interval, which is pretty cool. Here I've also shown you that it's not that we're achieving this by making the confidence intervals larger, which is a trivial way to do it. In fact, they're slightly smaller. So basically this works out. What have we learned? We have learned how to build bootstrap percentile intervals, and we have seen under what conditions they are guaranteed to work, which is where there exists this monotonic transformation that maps the estimator so that it becomes Gaussian. It's very important to realize that bootstrapping is not magic. You still need to carefully analyze the bootstrap confidence intervals to verify under what situations they're going to be valid confidence intervals, because there's this temptation to say, well, you know, we would like to sample from the population. Instead, we sample from our data, and that's kind of like sampling from the population, so things work out. You have to be very careful with those kind of arguments, okay? Here we have seen that things work out if the estimator is Gaussian, And things also work out if the estimator is Gaussian after a monotonic transformation if you use Bootstrap percentile intervals. And that's all I got. Thank you very much.